Okay, I hope that you are familiar with the concept of density. Yes? All right, and density is mass over volume, so you are responsible for knowing D equals m over v, density equals mass over volume. Are we okay with that? Okay, excellent. So just to give an example, sometimes this can either be like a lowercase d or it can be an uppercase D. You'll see it both ways. I'm not sure. I mean, really, the official symbol is the Greek letter rho, R-H-O, which looks like that, but people always think that's a P. It's not, it's a rho. So we don't use it, we use a D. You can use a big D, you can use a little d, I don't care. You want to use a rho? Use a rho. So. At any rate, so if I was to ask you about an iron's density, this is the first example there. I've just pulled it off to the side so I can write it. An iron bar has a mass of 19,600 grams and a volume of 2.50 liters. What is the iron's density? How easy is this question? Very easy. The only thing where you might get it wrong is you might just go like this. Start thinking about it. The numerator's wrong? Oh, didn't even notice that. Okay, that wasn't what I was going for, but yes, I just wrote that wrong. That was a typo. Okay, what else is wrong with this? Units. So we need to have grams, and we need to have liters, and we need to have grams per liter. Let me try this again. 19,600 divided by 2.5. See if I actually, oh no, it's 7,840. Okay, what else is wrong with this? Write the formula, yes. Okay? Because you want to show what you're solving for. That's going to be a half a mark. You want your formula. It's going to be a half a mark. You're going to plug things in. Half a mark. And you get your answer, your correct sig figs, with units. Half mark. Is good? Yes. Can you what? Why do you need to put the formula in? Because you are communicating to somebody else. You are not just doing it in your basement for yourself. Yes? No, we're assuming that it makes it much easier to read if I have a start to my sentence rather than beginning midway through. Yep. It's like using the word it. I can almost always guess what the word it means, but I shouldn't have to. Right? Yeah, but you know, like if I don't see it, besides which, it's not always going to be like density, like I've learned that since grade 8. Sometimes it's going to be like, you know, the coefficient of friction, which I have not learned since grade 8 or whatever, you know, it's just good practice. All right, now we can also use density as a conversion factor. In fact, you did this back in the conversion factor unit. So we have mercury, which has a density of 13,600 grams per liter. Now, when you see things written with this slash notation, what should you be doing? You should be rewriting it as 13,600 grams per liter, okay? Because that way it looks like a conversion factor. This way, it doesn't really look like a conversion factor. Technically, you don't need to write it this way before you put it in your equation, but some people don't think of, like when they go to write their equation, they'll be like, I don't know, I've got 425 grams per grams, and then they'll be like, I need to have my grams on the bottom, so I'm going to have 13,600 grams per liter, right? Because they don't know that the liter is on the... So I'm suggesting that you do this if you have problems figuring out that the liter should go up there rather than being there. Does that make sense? Okay, so rewrite it and then show me what you're solving for. We are finding the volume in milliliters. So we don't know the volume in milliliters. We are starting with 425 grams, and we are converting that from grams into liters. 13,600 grams per liter. And then we want volume in milliliters. So we would need to convert our liters into milliliters. What is the conversion factor between milliliters and liters? 1,000 milliliters are in 1 liter. And there may be some questions in here where it's not so easy as 1,000. You might need to remember your mega, kilo, deci, centi, milli, micro, nano, 631,236. 9 is for the nano. And remember, which ones are negative? Deci, centi, it's all the ones that start, it's just other than the first two, they're all negative. And what does it mean? It means that if I have a megagram, that is equal to 10 to the 6 grams, because remember the 1 goes with the prefix, right? And then the power of 10 goes with the regular gram. Yes, the 1 goes with the prefix, right? So you'll find in here there are some questions where you have micrograms or something like that, okay? And you might need to use these ones. Feel free though, if it's something easy like milli, to just, you know, use the easiest type of conversion factor. All right, now we're actually not going to stop there today because technically I could have assigned you any of these problems back in Unit 2. We are actually going to go on and figure out how density is related to moles. Okay? So this is now on page 71. So in the last problem we did, we converted grams into liters using density. So guess what? We can convert grams into volume by using the density. Okay? And this is not volume of an aqueous solution. What do we use when we're converting from moles? Like if we wanted volume of an aqueous solution, what would we use to convert from moles to volume of an aqueous solution? That would be molarity, the moles per liter. Okay, so you have to be careful. What am I asked for the volume of? Am I asked for the volume of an aqueous solution, then I'm using molarity. Am I asked for the volume of a solid, liquid, or gas? I'm going to use the density. The nice thing is, though, that the question is probably going to either give you the density or it will give you the molarity. So you'll be like, oh, I must be using the density here because they have given me the density. Oh, they gave me molarity. I guess I'll be using molarity. Yes, so it's not as challenging as it sounds. All right. Now, I chopped this out from the other mole summary page. Okay, so you can see we are focused in over here where we're converting between grams and volume of a solid, liquid, or gas. So let's take a look at this first question here. How many moles? So we don't know how many moles are contained in 23.0 milliliters of ethanol. So 23 milliliters, what can we convert milliliters into? Take a look at the question, see if there's any conversion factors in there. We only have one other number, yes? It is the grams per milliliter. So what can we convert milliliters into? We can convert it into grams because we have grams per milliliter. The other thing you can do is you can say, I have a liquid, yes? So I have the volume of a liquid, and I need to then convert it eventually over into moles, which means I'm going to have to convert it first into grams and then into moles. Okay? So we're going to convert milliliters into grams. Can we go from grams to moles? Yes, we can. So that is a how many step problem? Two-step problem. 1, 2. What do we use to convert between milliliters and grams? We use density. What do we use to convert between grams and moles? Make sure you tell your partner, what do we use to convert between grams and moles? Molar mass. Okay, so what we've got then is we've got, I don't know how many moles is equal to 23.0 milliliters times, and I want to cancel the milliliters and find the grams. And so I'm going to use this density here. 0.789 goes with the gram. So 0.789 grams per 1 milliliter. And we get, let's see what we get. We get, let's see, 23 times 0.789. Oh, hang on. Do I want to do that or do I want to go to moles next? I could do it in two steps, but why don't I just go to moles next? Okay, so my milliliters cancel. And now I want to go to moles. Where do I look to find the molar mass? On the periodic table. So we have 12 times 2 plus 6 plus 16. So 12 times 2 plus 6 plus 16 equals 46. So I have 46 grams per mole. I've done something wrong. Yes. Yeah, the 46 needs to have the correct sig figs. when I'm adding them up, I'm not really adding up 12 and 6 and 16. I'm adding up 12.0, 6.0, 16.0, and so my total should be 46.0. Remember, all of your molar masses should have a decimal place when we're using one decimal place when using our periodic table. Okay, so now we have 23 times 0.789 divided by 46 equals 0.3945, and the unit now is moles. Accept that. 3 sig figs, yes. 0.395 moles. Okay, what volume of aluminum contains 8.35 moles of aluminum atoms? The density of aluminum is blah, 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 blah. So we are starting with 8.35 moles. That's our initial quantity. We want to know the volume, that is our unknown, and we have a conversion factor. So we are starting with moles of Al. We want to finish with volume of Al. I'm guessing we want to use milliliters because they give us milliliters there. If you're not told the unit, you can choose whichever one is convenient based on the question. Okay, if you want to convert to liters, you could, but why? So if we want to go from moles to milliliters of a solid, here we are, here we're starting at moles and we want volume of a solid. What do we have to convert to in between? Grams, okay? So we're going to go from moles of aluminum to grams of aluminum and then to milliliters of aluminum. So let's take we want to find the milliliters of aluminum. We're going to take 8.35 moles of aluminum times, we're going from moles to grams, so we want moles on the bottom, cancel out, and grams on the top. Molar mass of aluminum is 27.0 grams per mole. So now moles have canceled out, we have grams, so we want to cancel the grams and find the milliliters. And so now we have to go back to our density and say what number goes with the milliliter and what number goes with the gram. 2.70 goes with the gram, and since there's nothing with the milliliter, you can just write 1. Okay, so 2.70 and 1, and we get 8.35 times 27 divided by 2.7 equals 83.5, and our unit that we are left with is milliliters of aluminum. Is good? Okay. So if you are not taking Chem 12, oh no, that's right, everyone in this block is taking Chem 12. Never mind, I have my other block where they are. Okay, so we are going to go to dilutions 2, and we're going to talk about acids because we didn't get to there last day. So this is in dilutions 2 on page 5. In And if you were away last day and you needed dilutions too, right here. Is there anyone who's away? Okay, and this note that we have is about acids. When a lot of water is added to a concentrated acid, the mixing process can be very exothermic. Have you heard the term exothermic before? What kind of a reaction is exothermic? What does it do? It releases heat. So a fire is exothermic. A firework is exothermic, okay? And if you take concentrated acid and you pour water into it, that mixing process actually generates a lot of heat. Problems with that is sometimes if you have a very fast change in heat, it can cause the glass to crack, okay, which we don't want. Or it can cause the mixture to boil because it's released so much heat so fast that the mixture boils and then it's spattering upwards and you're like, concentrated acid. So it's not good, okay? I'm actually exaggerating. This doesn't really happen that much, but it's something you're expected to know, so there we are, okay? Like, honestly, like, you'd have to be pretty, anyway. You won't be working with acids that concentrated, but you have to worry about it. But let's just pretend. So what you're going to do is, this is the dilution of the stock solution, and if you remember, last day we said we would start with our stock solution. What kind of a solution is a stock solution? It is highly what? Concentrated. Okay? Highly concentrated. And we're going to take a sample of that. So we're going to take some of that. Okay? I know they don't come out as squares, but we're going to pretend. And then we're going to put it into a new container. This is how it normally works. And what kind of a new container might we put it into? We might put it into a volumetric flask. Okay, so now we have our stock solution. And what would we do after this? We would add water. So you're going to transfer the correct volume of stock into the volumetric flask. And then you are going to add water to the line, which is the final volume that we want. Okay, so we've now added water to the line. Now this is all well and good if we're not working with an acid, because if we start adding water, it can do what? Explode, crack the glass, blah, 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 whatever. So what we're going to do instead for an acid, we are first going to fill the volumetric flask partway with water. Okay? And the nice thing about water is water has a large heat capacity. Do you guys know what heat capacity is? It means if there's like a big difference in temperature, the water will absorb a whole bunch of the heat, and so it keeps the temperature relatively stable. Okay? So that water that is already there has quite a large heat capacity, and so as the heat is generated by the reaction, the water just gets warmer, but because there's so much of it, it doesn't get warmer very fast. Does that make sense? Whereas before, when we had our concentrated solution down here, if you add a little bit of water, there's not much volume there to absorb the heat, so the temperature will rise very quickly. Okay, so first we're going to fill the flask partway with water, and then we're going to add the acid. And then finally, we will finish filling to the final volume with water. Okay, so this is a regular solution. Now we're going to say what happens with an acid solution. What we're going to do is oh, I haven't left myself enough room, have I? Let's do it over here. Acid solution. We're going to take our flask, and what should we put in it first? Water. Okay, so water first. Maybe halfway full, maybe 2/3 full, something like that. Okay? What are we going to do second? Now we're going to add the concentrated acid. I know it doesn't come as a square. I should be drawing a volumetric pipette, but drawing a volumetric pipette is difficult. Drawing a square is easy. Okay, so here comes our concentrated acid. That's number 2. Add the correct volume of concentrated acid. Okay, and that is going to be now in here, yes? So now we have that and we swirl it. All right, and now it hasn't gotten too hot. It may get a little warm, but it doesn't get too hot. And then finally, what we're going to do, what do we do last? Add water to the line. What should you use at the last tail end of adding water to the line? Use an eyedropper. Okay, so now we have finished adding water to the line. The line there, okay. So water, acid, swirl, add water to the line, and then what should we do as our last step? It was your last step when you made your solution yesterday. Stopper, flask, and invert to mix. Okay, so you are responsible for knowing this procedure for the acid. You're responsible for knowing the procedure for a regular solution. You are also responsible for knowing the procedure that we did yesterday. So, you were away yesterday. You will want. So, what we do when we're making a solution from scratch. Why don't you guys take 1-2 minutes to make beautiful drawings just like mine that show how you make a solution from scratch, starting with solid. Okay? So grab a piece of paper, draw how you would because literally this is pretty much what I'm going to ask you on your quiz. I'll be like, give me a little labeled diagram showing me what you would do. And you know I can't draw, so it doesn't have to be pretty. So even if you were, oh, never mind, I'm just talking to myself now. Now remember, your drawings don't have to be good, because you can see my drawings are pretty crappy, but I did it pretty quickly, yes? Because I don't want to spend all day doing this. I don't want to be on my quiz going like, oh, I need a ruler to make my scale. I can just label it scale, and it can look like any old thing. It could look like this. I could have my scale look like that, and as long as I label it scale, it's all right. Okay, it's not really great to have a scale that looks like that, but I could deal with it. So we add the solid solute. Here it goes. To the correct mass. We then transfer the solid to the flask using a powder funnel. Now our solid's in the bottom, and we add water to about 1/2 to 3/4 full, and then we swirl. Okay, my pen's not working anymore. That's good. Okay. We swirl until it's all dissolved, and then finally we add water to the line, and then we stopper it, and then we invert to mix it. And see, even though step 6 is above step 5, because they are numbered, I know what order they're supposed to go in. Yes? Okay. So that's pretty much it. You should be reminding yourself of that over the weekend, as well as the procedure for diluting. Now we are also going to do a quick review of how to prepare a solution by diluting. Do you think you guys could try this one on your own? Do you want to try it? Describe how you would prepare 250 milliliters of 0.025 molar HCl solution from a stock solution with a concentration of 8 molar. This is not a question you have on your page. I am sorry. I meant to include it, and then I did not get around to it, so you'll just want a piece of paper. Okay, there's actually, I think the last page is your plan, so if you want to use that. And remember, steps 1 and 2 are the math steps. So start by just doing the math. Sometimes all you'll be asked to do is the math. When in doubt, what should you find? When in doubt, find moles. describe what you would do with that. Nowhere. So what you have is that molar under it now. Okay. Thank you very much. So those are really, that's the information you're starting with. And so you want to start there and find let me what do we need to find out about the stock solution? I need to know how many moles I need of this in the stock solution. So but I need to know, I'll get the moles from here, right? But then I need to say, how much of this do I need? To get X moles, okay? And when I say how much, what would I mean? It's a solution. So when we say how much, we mean volume. know I have a solution of hydrochloric acid. So I'm not trying to find grams of hydrochloric acid. I'm find volume. This was beautiful. Find moles of this. Yes. Yes, of course. Yes. Mm-hmm. Yeah. So if you're still stuck, don't worry, we'll do this together. What we're trying to do here is we are trying to find the number of moles that we want in our dilute solution. So the number of moles is what we don't know. We are starting with 0.25 liters. That's our initial quantity, and our conversion factor is the 0.025 moles per liter. Okay, so 0.25 times 0.025 equals 6.25 times 10 to the negative 3 moles. If I know the number of moles, and I know the concentration of the stock solution, can I find the volume of the stock solution? So if I now know 6.25 times 10 to the negative 3 moles, and I know that the stock solution is 8.00 moles per liter, can I find the volume? Yeah? Okay, because what I can do is I can say I want to find the volume, and we're starting with 6.25 times 10 to the negative 3 moles times 1 liter per 8.00 moles, because I want my moles to cancel. And we get 6.25 times 10 to the negative 3 divided by 8, and we get 7.8125 times 10 to the negative 4 Liters. Now, does it make sense to keep that as liters, or do you think we should change it to milliliters? Would it be easy to measure out 7.8125 times 10 to the negative 4 liters? Probably better to change it to milliliters. So we could say times 1,000 milliliters per liter, and we get 0.78 milliliters. That's still a really small volume. But that's how it works. Okay, there is practice in there. Your homework is to go home and work on 8.4b, which is dilutions 2. You've done the first two questions, or at least in theory you have. If you haven't, then do the first two questions. And they kind of walk you through it. Okay, the first two questions kind of walk you through it. Like they're like, find the moles, find the volume. Then what do you do? Find the moles, find the volume. Then what do you do? Okay. You should be finishing up anything that's left in dilutions 1, so you feel good about that. We have dilutions 2, we have dilutions 1, and then finally we have 5.3c. Because that's all the molarity, particles, grams calculations. Liters, grams, moles, particles. And lastly, but not leastly, for your quiz, you should also be looking at you could do some of 5.3a. Actually, there's two more things. 5.3a, that's fairly straightforward. It's just finding molarity. And finally, 5.4b. Okay? And also the procedures. I won't give you anything on density because I think this is enough to keep you busy for the weekend. Yes? Uh-huh. Yes. Yeah. We'll give you some density homework like after the quiz. You can work on some density. All in one line. Absolutely. Do it all in one line. Yeah. Yeah. Yes. Yes, 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 yes. You tweet it to you. My brain is a little slow, you know. Probably, yes.
Do I need?
You're welcome to have one of those if you want it, yeah. Yes, certainly, yeah. Yes, yeah. I left out B, but I don't know why I left out B. I mean, it's just kind of like C, but just a little bit easier. So if you're like, it's all easy, you can just move on to C. Does that make sense? Okay, so all of 5.3. Make sure it's 5.4B that I want to give you. I think it is. Oh, no, not 5.4B, 5.4C. Oh, so sorry. Write down 5.4B. It's not 5.4B, it's 5.4C. That's the molar mass. That's the part that's on the quiz on Monday, okay? Now, just so you're aware, I'm not going to ask you all the procedures because that would be a lot of writing. I'll just ask you one of them, but you won't know which one. Okay? Yeah. But definitely it's too much writing to write them all.